short video. Not because it's not much material to cover, but mostly because this is one of those topics that is kind of unteachable. Some folks are just a lot better at visualizing things in two-dimensional space than others, and symmetry is one of those things. So, what does it mean to be symmetrical? Well, there's some good examples here. Basically, symmetrical just means that one side is equal to another. Um, in this case, we're going to talk about, we'll start off talking about line symmetry or reflectional symmetry, where like something is, part of it is a mirror image of the other part, right? So um, humans and a lot of animals. I go back to biology examples, right? In biology class, hopefully you learned about how some living things have bilateral symmetry, right? So things like a fish, it has a fin on left side and right side. It has an eye on this side and this side. Humans have bilateral symmetry. Um, Same deal. We got an ear on both sides and an eye on both sides, and our mouth is symmetrical, etc. Um, Whereas something like a jellyfish might have a different type of symmetry. So for these guys, we have lines of symmetry, and a line of symmetry is just where that mirror image, that line of reflection would be. So in this case, the mirror image line would be here. Their example is tracing paper, because then you can fold the paper in half, right? Little kids learn how to do this. They fold the paper in half and then they cut out a heart. So we'll just skip right ahead here. To part D here, look in your book for the figures. I covered them up. But go ahead and see if you can draw all the lines of symmetry on these figures, right? So think about not, cutting things in half evenly, but cutting them so they're exact mirror images on the other side. And then add up all those lines of symmetry. So pause it here while you figure it out. I'm going to go ahead and reveal all these. You could, some people might look at this one. Let's see if I can get a line here. And they might say, oh, look at that. There's a line of symmetry right here. The downside of this is that you're not cutting this angle. This is a 90-degree angle, right? So here's a rectangle. You're not cutting this angle exactly in half. And as it turns out, if I were to reflect this, I need to dig out something, but it would look something like this. The short end of the rectangle is here, the long end of the rectangle is here. So if I were to reflect it, you see how this is like a reflection here? I've reflected that over. So therefore, this bottom part, this one ranks weird. I can move them though. No, oh, I messed that up. So this bottom part here, when I reflect it over this line of symmetry, it ends up being in a different spot. So this isn't a line of symmetry. But these pink ones are, right? Because if I take this half over here and reflect it, then it's in the exact same spot. So for this one, we have two lines of symmetry. For this one, you can kind of make an argument that there's a line of symmetry here. As it turns out, they're kind of, it's hard to visualize, but I'm not sure the angles are 90 degrees, but whatever, either way. And then for that last one, there's only one possible line of symmetry. So it is possible for there to be multiple lines of symmetry. A circle has infinite lines of symmetry, right? Okay. The second part is rotational symmetry. Again, going back to our biology example, mammals and fish and birds and a lot of things have bilateral symmetry, but some things have rotational symmetry. Examples would be like hydras and jellyfish and sea anemones and stuff like that. So, oh yeah, starfish. That's a good example. Rotational symmetry, right? So in these guys, essentially we can take this figure here. I don't know if I can draw a star. They don't have stars, do they? I do have stars, but I don't know if I can make them. Whoa, here's my star. Well, that wasn't bad. See, there's a star. And then I can rotate it. So I'm going to rotate it, and I get the exact same shape, right? And I rotate it again, and I get the exact same. Note that you don't notice it rotating, right? As long as these points are indistinguishable from each other, this is indistinguishable, assuming I line it all up from that, right? It's the exact same thing. So don't think, oh, yes, it's the same shape, but no, it hasn't been rotated enough for symmetry, right? Symmetry has to make it line up perfectly. So in this case, we have rotational symmetry. We have 5 different ways we could rotate it. So how many ways are there, or how many degrees are there in something rotating all the way around? It's 360. So 360 divided by 5 is 72, as it turns out, because that's 1/5 of the way around. That's 1/5, 1/5, 1/5, 1/5, and then 1/5, for a total of 72 degrees each one. So that's a calculation you should be able to do. See if you can do part B here. So pause. The cake is a lie. For this one here, again, the square, we can rotate it. We're going to leave out the 0 degrees and the 360 degrees because those are the obvious ones, right? We'll ignore that. What we are concerned about with this is square. We know this is a square because all these side lengths are the same and they're all 90 degrees. So we can rotate a square 90 degrees and it still looks like the exact same square, right? It's indistinguishable. For this one here, again, you have a pointy end here, so therefore, if you have a pointy end, there's no rotational symmetry you could do. This one's a double-ended arrow, right? So both ends are the same. They're indistinguishable from each other. Therefore, we could rotate it 180 degrees. Okay, and that's it. So good luck.